Hello everyone, in this video we're going to go over some of the problems in equations and identity that we have in the review for the exam 3. So on equation number 1 we have one of the typical equations that have been working for a while. This type of equations that we always talk about not canceling the sign because we will miss a lot of information that we get from the sign. Notice that we also going to get the solutions only in the interval 0 to 2 pi. We could potentially get more solutions if we're not restricting to this interval, or we can potentially get less solutions if we are restricting this interval even more. Okay, so let's go ahead and get started. So we have sine of x here times tangent of x, and we're going to move this sine of x to the other side to leave one side to be equals to 0. The advantage of having one side equals to 0 is that we can contrast what this side is going to be with respect to this one. In this case, we can use the law of the real numbers that says that if a times a is equal to 0, then either a is equal to 0 or b is equal to 0. And that's going to make sense here because we can factor sine of x out of tangent of x minus 1, set that to be equals to 0, and so that will give us two scenarios. Sine of x is equal to 0, or tangent of x minus 1 is equal to 0. So that will provide me with sine of x equals 0, or tangent of x equals 1. Now the individual solution of this in the interval 0 to 2 pi are going to vary. So for example, sine of x is 0, where x is equal to 0, pi, and 2 pi. And of course, we remember this from our special angles, similar to the information that we get from tangent. From our special angles, we know, or the definition of tangent as well, we know that tangent is sine over cosine, right? And so if tangent of x is equals 1, that means that sine should be equal to the cosine in this case. And that's going to happen in the unit circle only in two places. And that happens when we have pi over 4, right? They have to have the same sign, by the way. So that's going to happen here at pi over 4, or it's going to happen at here in 5 pi over 4, where they're both negatives. Okay? So we have the solution is pi over 4 or 5 pi over 4. Now, equation B has cosine of 2x plus sine square of x. So the key takeaway from this is that we want to reach a single expression with no sums equals to a number on the other side. So we will use any identity that is useful. And remember, we have a formula sheet for a lot of these identities. So I have one in the solutions. In the solutions, we use 1 minus 2 sine square. But in here, I'm going to use a different one. So I'm going to use cosine of 2x is cosine square of x minus sine square of x. So this one is cosine of 2x. And then plus sine square of x equals 0. Now notice that I can cancel the sine square right away. And so I'm going to get cosine square of x is equal to 0. Now because this side is equals to 0, then I can very easily just say, oh, okay, so cosine of x gotta be 0. Because I don't care about doing plus or minus here since it's 0. And cosine of x equals 0 is going to happen on 0 to 2 pi in 2 points, pi half and 3 pi half. Remember, on the unit circle, the points, if the unit circle is points of the form cosine of theta, sine of theta, the cosine of theta being 0 means the x coordinate is 0, and that happens here and here, where x is equal to 0. And that is the angle pi half and 3 pi half. Right? Now, that is not going to occur in the next scenario. if we have tangent square of x minus 1 equals 0, this means that tangent of x, tangent square of x is going to be 1. And so this means that tangent of x can be either 1 or it can be also minus 1. Okay? We already saw the solutions to tangent of x equals 1 in exercise number 1. That's going to be when it was pi over 4 or 5 pi over 4. So tangent of x equals minus 1 means that the sine and the cosine are being equals minus 1. That means that the sine and the cosine, they have the same value, but they have opposite signs. And so in the unit circle, pardon my circle here, that's only going to happen in 2 points. Opposite signs occur on the second and in the fourth quadrant. And they're multiple of pi over 4, because remember, the only place where sine of x and cosine of x are going to be equals is going to be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, which is all the pi over 4 multiples. In the places where it's opposite, it's in 3 pi over 4 and 7 pi over 4. So what happens in the second quadrant and what happens on the fourth quadrant. And those are the solutions for C. Now for D, it's very similar to B. We have a double angle identity. So what we do is we decompose this in the double angle identity, just in terms of sine and cosine. Then after that, we can move sine to the other side. And then we can factor sine again. So we get sine of x, 2 cosine of x minus 1 equals 0. And that's going to give me two equations. Sine of x is equals 0, or cosine of x is going to be equals 1/2. And so that's only going to happen. So we already saw what happens with sine of x equals 0. This is 0, pi into pi in this interval. Cosine of x equals 1/2 is the new one, but that's also going to happen in 2 places. So cosine of x equals 1/2 means that we're over here. Remember, the cosine is the kind of x coordinate of the plane. So if cosine of theta is 1/2, we have this line over here, and I have one angle that is happening here on the first quadrant, and that's going to be pi over 3. And I'm going to have one that is going to be in the fourth quadrant. And so for the fourth quadrant, if this is x1, for the fourth quadrant is going to be 2 pi minus pi over 3. So this is 6 pi over 3 minus pi over 3 is going to be 5 pi over 3. And so that is the solution for the equation sine of x equals sine of 2x. Now, if I go again with this type of equation where sine of x is equals cosine of 2x, then I gotta be careful on looking what type of information can I get. Since I have sine of x, it will be good that I at least have things that are in terms of sine of x. So the best thing that I can do from the different identities that I have for cosine of 2x is I can put everything in terms of the sine. So I can go 1 minus 2 sine square of x. And so what's going to happen with this is that I can move this to this side. All is going to be moved to one single side. And now I'm going to have 2 sine square of x plus sine of x minus 1 is equal to 0. So notice that this is like I have a quadratic equation. So if I say, well, let's make u equals sine of x, so this will be 2u squared plus u minus 1 equals 0. Okay? And so once that I have that, then it's just a matter of factoring what I have over here. And finding the solutions that I can have. So this can be this polynomial here can be factored as 2u minus 1 times u plus 1. You can verify this by multiplying. This is 2u by u, 2u squared. Then this one is 2u minus u is 1u, and minus u times u is just u. Okay, so once that I have this product equals 0, then I'm going to have essentially 2u minus 1 equals 0, or u equals minus 1. Getting back to what really u is, this means that sine of x should be equals 1/2, or sine of x should be equals minus 1. Okay. So now I can go for the points where this happens. So sine of x, if you remember your special angles, sine of x equals 1/2 occurs with pi over 6. And also e occurs with 5 pi over 6. Okay, remember this is a y value that is being positive, so that means that in the unit circle that is occurring on the first, and also is occurring on the second quadrant. And for sine of x equals minus 1, that's only going to occur in a single place. That's when the height y is minus 1, so it happens when the point is here, the y is here, and so that's when x is equals 3 pi over 2. All right, so for this equation we ended up having 3 solutions. Now, equation f is an equation that is in terms of sine and cosine, but in here there's not a lot of ways of really simplify this, so I gotta go the opposite ways. In here is much more easier to write this as 1 plus sine of 2x equals 0, and so I'll be having sine of 2x equals minus 1. And so because we just saw that sine of x let me see what happened with sine of x is when sine of x is minus 1, so this means that 2x gotta be 3 pi half. This is actually a little bit different from what we have on the key solution. That this is probably be the more correct answer to that. So really here you will have that this is 3 pi over 4. That will be our solutions. So I'm noticing that there's probably a typo on the key that we have from before, because we're not getting a minus. If we have a minus here, then it will make sense what we have in the key. But for that, this is a good solution for this. 3 pi over 4 is still on the interval 0 to 2 pi. Now, for this one here, we have 1 minus 2 sine squared. And again, this is very similar to what we have before. This is cosine of 2x equals square root of 3 over 2. And this is going to happen when 2x is equals pi over 6. But we can check for some more points where this happened. So 11 pi over 6 is also a point in 2 pi. But notice that we're going to divide by 2 later. So if I do this, I get pi over 12. And I get 11 pi over 12. But this is barely getting to pi. So notice that 12 pi over 12 is only covering up to pi. So probably I could get some more solutions. So the next point where it's going to be square root of 3 over 2 is going to be 13 pi over 6 and 23 pi over 6. Notice that this are outside of 0 to 2 pi, but when I divide by 2, they fall inside of 0 to 2 pi. So with this scenario, we actually have 4 solutions here. All right, and so that concludes the part of equations. Now, for identities, remember that the trick is always starting from one place to get to the other. So let's go ahead and do this sine of 2x over 2 sine of x. So this seems to be the more complex piece. And what we're using here is the double angle identity. That, again, this is in our formula sheet, so it's just a matter of applying our formula sheet. You replace this by what it is here, we get to cancel the sign, and we cancel the 2, and we get cosine of x. So we reach from one side to the next. Now, for b, we have cosine of 2x over cosine of x plus sine of x. And so now we can split this apart into cosine square of x minus sine square of x. And this is going to be this little piece here. This is directly this. But now, if you remember, when we have a difference of squares, we can factor this as a minus b times a plus b. And so this is cosine of x minus sine of x times cosine of x plus sine of x. And so now you can see what's going to happen. And is that this is going to be canceled with this, and the only surviving things is going to be the cosine of x minus sine of x. Now, in equation C, we do a similar thing, but here we could probably benefit from just breaking apart the cosine. The cosine in terms of something that get rid of the sum. So here we're gonna say sine of 2x over 1 plus cosine of 2x is the top we can break apart as 2 sine of x cosine of x, and the bottom we can break apart as 2 cosine square minus 1. Since this identity is going to give me a negative 1 that I can cancel with this, and so now I'm going to have 2 sine of x cosine of x over cosine square of x times 2. So now the 2 gets to be canceled with the 2, and I get sine of x cosine of x, and I can split apart that cosine square as cosine of x times cosine of x. So you can see that I can cancel this and reach the other side of the identity. So the trick here was recognizing that one way of getting to cancel stuff was eliminating this one. So after that, it's just a matter of picking the right representation for cosine of 2x, and then from there we can go. Now for D, we have the difference between secant and tangent. And of course, because this is in cosine and sine, then the trick is going to be rewrite each of these identities in terms of sine and cosine. So we have 1 over cosine minus sine over cosine of x. Now we just work on with these two fractions, and this becomes cosine of x minus sine of x cosine of x over cosine square of x. Now, however, I can see cosine square of x as 1 minus sine square of x, and I can factor the cosine here, cosine of x, and leave 1 minus sine of x. So you can see that if I do the difference of the squares, I'm going to be able to get this 1 minus sine of x. This is 1 plus sine of x, 1 plus 1 minus sine of x. And so I get to cancel this too, and I reach the other side of the identity. Last but not least, we have this in terms of cosecant and cotangent. And one way to go about this is just essentially transform everything in terms of whatever we can get in terms of sine and cosines. But since I see cotangent square, I'm going for first multiply this and distribute this. Remember that cosecant is 1 over sine, so I got the impression that this is going to cancel with this. So I'm going to get cosine square of x minus cosecant of x times sine of x. Notice that at this point, this is 1 over sine times sine of x, and so I get to cancel this out, and we get cosecant square of x minus 1, which by definition is pretty much cotangent square. Okay. You might be wondering why cosecant square minus 1 is cotangent square, and you got to remember that this is coming from the basic identity, sine square plus cosine square equals 1, and then you divide everything here by sine, and so sine square divided by sine square is 1, plus cosine square divided by sine square equals 1 over sine square. And so this is 1 plus cotangent square equals cosecant square of x. And so that means that cotangent square of x is cosecant square of x minus 1, which is what we use over here. Okay? So that finished this part in equations and identities.